like to now hand over the stage to Mr. Ayman. Thank you.
Okay. Thank you, everyone. And I've been always criticized since yesterday that I didn't practice any type of democracy. So I will try to do one now before we conclude. So I will give you the option either to cancel the break or to cancel the lunch. I know this is it's not a bit much of democracy, but this is what I can do. Okay, if you allow us to continue and proceed in order to catch up with the timing and the schedule of the day, otherwise we will really miss the lunch because the restaurants after 3 o'clock cannot serve the lunch. So we'll need to be there at the restaurant by 3 o'clock because they will be removing it by 3:30. 30 minutes will be the minimum time needed maybe for the lunch. So if this is acceptable, we much appreciate your cooperation and understanding. And we would like to proceed directly to the next session about the standards testing and relevant requirements. And luckily we have a shorter session this time. It's only 3 presentations, so we can go maybe quicker a little bit. Of course, you have the liberty to go outside, bring your coffee, and come back if you need. But don't do it as a group. So for this session, I would like to ask Dr. Karim Amran from AHRI and Mr. Kazuhiro Sato from Jaraya to help us in moderating this session. Thank you both. Please, the floor is yours.
Good afternoon. Since we are running out of time, I'm going to be quick. This session 6, is on standard and testing. So we'll be focusing on that subject and basically to look at the code and standards for the safe use of alternative refrigerants. We've heard during the past 2 days about alternatives, and I think it's apparent to all of us that most of the refrigerant that are being proposed are either flammable or mildly flammable. So in order to use these refrigerant safety standards and codes are being amended, in particular to accommodate the 2L classification or the mildly flammable classification. So this afternoon we're gonna hear from the work that ISO has done to accommodate this 2L classification, and we will also hear from ASHRAE and what the standard ASHRAE 15 has been doing to do the same thing. And finally, we will hear from, we get the perspective of a testing laboratory on issues surrounding with the testing of alternative refrigerants. So as with the other session, we're going to hold the questions at the end of the session. And now I would like Mr. Sato to introduce the first speaker.
Hello, everyone. I'd like to introduce the first speaker very briefly. I think you're waiting for lunch. Okay, our first speaker is Miss Else Bird. She is a working member of ISO TS 86 SC1, Working Group 1. And she is from Belgium and working for Daikin Europe. And she's working in Daikin Europe since 1989 and manager regarding eco-design and product safety. And she also acts important role in the standardization work, expert for ISO TS 86, as I mentioned, and some other standardization work. Okay, let's welcome Else for the first speakers.
Thank you, Mr. Sato, for the nice introduction. Thank you to the organization for inviting me to speak here and to present the situation in ISO. I just need to find out how this works. So next is here, a pointer there. Okay, thank you. So I just give a very short introduction here, and I'll try to move fast because it's a rather deep technical subject, but I would like to have everyone be clear on the requirements that are set in 5149. So first of all, we have a big need for alternatives. I think everyone has talked about it already today. And we should understand that when we want to convert to lower GWP refrigerants, it also means that the refrigerant is less stable. If it's less stable, it means that it is more toxic or it is more flammable. It's a natural fact. So for that matter, we have to modify the standards, and we have to prepare them to allow for safe use of these refrigerants. And we have two major standards on the international level that are ready or are being modified, and that is ISO 5149 and IEC 6335-2-40. So today I will explain to you what happened with 5149. As we can see that as of this year, it has been published. So 5149, the old version, existed in 1993 and has been modified now in 2014. The old version didn't allow flammable refrigerants for human comfort. Today, we have a standard that allows the use of flammable refrigerants, of course taking necessary safety precautions. They consider toxicity and flammability characteristics to determine the refrigerant charges. And there are also introduced here clear requirements for 2L and also for multiple evaporator requirements. I also need to emphasize the 1993 version was one part. Now we are talking about 4 parts. Part 1 will define, set the definitions, will make classifications and set the requirements for selection and charge limits. Part 2 will specify how you need to design a product to be safe. Part 3 is talking about the installation site, and Part 4 will explain the requirements for maintenance, recovery, and repair. Now, to introduce, I will explain each part very briefly, but the first and I think the major part that is relevant here today is, of course, Part 1 and how the charge limits are defined. The charge limits are based on 4 main pillars. First of all, the characteristic of the refrigerant. The second one, where is the system located? The third one, how is the system set up? And the fourth one is the application. I will go through each pillar separately just to highlight what it means. First of all, I want to explain, of course, what is the refrigerant characteristic. We all know that we have the ISO 817 standard that is published today with the current classification that is on the screen. Yeah. So we have the 1, 2L, 2, and 3 defining flammability from no flame propagation to higher flammability. We also have A and B increasingly showing the hazard for lower toxicity and higher toxicity. What does it mean in terms of the refrigerant currently listed in ISO 5149? I show you here an overview of all the refrigerants and how the classes are populated. So you see that we are clearly working with a lot of A1s and that these are listed clearly in the standard. And you see that when we go to 2L and 2 and 3, that there the options become more limited. Now to go to the second pillar, which means the location classification, we have 3 classes. We have location A, location B, and location C. Location A is actually the general occupancy, and it explains it's actually the occupancy where people reside or are limited in their movement. So it means location A is about residences, hospitals, prisons, schools, lecture halls, and all types where people move freely around. In location B, we call it supervised occupancy, and there's always one person available that is aware of the safety precautions on site. Usually these are buildings such as offices, laboratories, places of general manufacturing. And then we have also location C, which is authorized occupancy. And these include actually facilities where everyone is aware of the safety precautions. We call these chemical factories, food factories, ice cream storage, all these type of applications or buildings are considered to be authorized occupancy. Then we have the third pillar, which is system classification. So they are subdivided in 3 classes. Class 1 is a system where all refrigerant containing parts are placed in the occupied space. So these are in general the fridges, the wine cabinets, portable units, or that type of product. We have also system class 2, where the compressor and the pressure vessel are in the machinery room or in the open air. Typically, these systems are split air conditioners, split heat pumps, multi-splits and condensing units, and probably a lot more than is listed here. We have also class 3, where all refrigerant containing parts are in a machinery room or in open air. In this case, I look at chillers, monoblock heat pumps. These are these type of systems that are in that classification. And then we have also classification 4, ventilated enclosures. Usually this is used for specific special product designs that require special measures. Now going further, we have also pillar 4. It's a subdivision between human comfort and other applications. Now this is just what is used for human comfort and what is not used for human comfort. A subdivision that is there but will be phased out in the future. Now if you look at the standard has a specific table which most people tend to find very complicated, and I show you here kind of summary of the table. So the table consists of what the refrigerant characteristic is, what type of occupancy the requirements are set for, if it's for human comfort, for other applications, and some kind of exceptions. And then also they are subdivided in the 4 categories for location classification. So you can see on the screen very clearly, I'm sorry, I don't know very well where to look. Oh, wrong button. So you can see here for the class 1 and 2, the charge limits will be explained later on. We have class 3 for chillers. And generally, there are no charge limits apart for flammability class 2. And then 4 has also specific requirements, but due to time constraints, I will not explain it in detail. So now to come back to the class 1 and 2 charge limit calculation. So we should understand that for all the refrigerants 2, 2L, and 3, all the charge limits are capped. And we use a cap factor. In some cases, people will have probably heard, I don't know, about this cap factor of 1.5. And this slide explains actually the differences in these caps. A cap factor has been introduced to differentiate between the risk of R290 and A2L refrigerants, and for this one we have compared it to R32. We have used a cap factor of 1.5, saying that actually the risk of 1 kilogram of R32 is 1.5 times less than 1 kilogram of R290. This is of course a very conservative approach because we have seen already in former presentations that the risk between R32 and R290 is far greater. It can go up to a factor 8. Now I show you here what this relates to in terms of refrigerant charges. So if you look here, when you apply it for R290, we have a cap factor of 1. It means that the limit will always be, if it's based on M1 on 150 grams, 1 kilogram for M2, which is 26 times LFL. And on M3, it will be 5 kilograms almost. For refrigerants, 2L refrigerants, and here I took the example of R32, you see that the limit is different. With the factor 1.5, you can apply 1.8 kilogram as a final limit, 12 kilogram for M2, and 60 kilogram for M3. Now, how does this relate to the further charge limit calculations? I will explain later on. Now, when we define the charge limits, we have seen already, Nasser has already introduced this formally and some other people have done it as well. So when you define the charge limits for 2, 2L, and 3 refrigerants for system class 1 and 2, there are two main approaches. The one is for human comfort and the other is for other applications. And for human comfort, we use this formula, this wonderful formula. And this formula actually is there because it considers the stratification and the mixing in the air of the refrigerant when it is released from an indoor unit. So the higher the leak occurs, the more it mixes in the air, so it means the risk is reduced, so you can use more charge. If it's installed, the leak occurs lower to the floor, then you get more stratification, the risk is higher, and in that case you have to use a lower charge. So I will clearly show it in the graph later on. Yes, thank you. Other applications use a very general formula. They use the rule of thumb of 20% LFL times room volume. And also all these charge limit calculations are capped. Now for the human comfort formula, we see that there is a clear relation between the room surface, the height factor, and the lower flammability limit. So this relates in this following graph. I will explain it to you in detail. So you can see here the correlation between the room area and the charge limits. The blue lines are actually the formula of human comfort. So you can see a clear difference between an indoor unit installed at 0.6 meters or a ceiling mounted unit at 2.2 meters. For other applications, we have the orange line, and there you see that this is more a linear curve that then is capped off also at the cap factor at the highest charge limit. I took the example for R32 here, just to be clear. Then I made a calculation for 3 typical refrigerants in ISO 5149 just to show you how it relates to 2 and 3. So you can see clearly here that this is the limit for R290 in the green lines, for R152A in the red lines, and then the blue lines for 2L refrigerants in general. These are the lines that are used for, and that are the charge limits when you compare charge to floor area. There is also an additional possibility to apply an alternative risk management system. There, when you have multiple evaporators, you can use more charge if you take specific safety precautions. Now, you can do that by making a robust design of the system and taking care of the installation. And then you can even go beyond that charge by taking several safety precautions. I will move a little bit faster on this one and just explain that shortly. So this translates actually to the following charge limit calculation. So the blue line, I apologize, I don't see this slide very well. The blue lines actually show the limitations when no additional measures are taken, as I've explained, the charge limits for human comfort. We can exceed these charts when we take special precautions on the design by applying the RCL value, the refrigerant concentration limit. And then we can also exceed the RCL value, the QLMV value, by taking at least one additional measure, for example, to apply ventilation in combination with the gas detection device. And you can exceed these charges even more if you at least take 2 safety precautions, for instance, a ventilation, a safety shut-off device in combination with a detector. I also made a comparison to compare the impact of the charge limits on high ambient conditions. I made an example of a 40 square meter room, and I compared R32 with R290 in comparison, and then calculated the charge limits for that room. As you can see, we have 2 effects that we have to consider. So when we install a system in such a room, then we know that first of all the load will increase. So if you compare it from medium ambient temperature, where we have 100 watt per square meter, we can expect in high ambient temperature 250 watt per square meter. We also know that the refrigeration capacity will reduce. So the charge in kilograms per kilowatt will also reduce from 0.24 to will increase from 0.24 to 0.28. And for R290, we took 0.11 and it went up with 15% to 0.13. Now, if you look at the graphs, you can clearly see that actually when you calculate the charge that you need in that room for, in this example, R32, you need 1 kilogram on medium ambient and 2.6 on high ambient conditions. But the limitations are the same everywhere. So you can see that actually there are limitations for floor standing types for R32 models. If you then look to R290, then you see we need actually in medium ambient conditions 0.44 kilograms, but in high ambient conditions we go to 1.04 kilograms. If you look at that, you see that all types of models from floor mounted to ceiling mounted are not able to be placed on the market unless we find means, of course, to reduce the charges significantly. I also want to explain what the requirements are for chillers in detail because I think it's necessary to know. They are categorized as system type 3. In general, there are no restrictions except for flammability class 3 refrigerants. And also you need to know when you install a chiller, it has to comply with the machinery room requirements in part 3 of the standard. And here I give you the values for the charge limits that apply to chillers. So for general occupancy, maximum 5 kilogram can be used. Supervised occupancy, maximum 10 kilograms. And there's no restrictions on authorized occupancies. There are other safety requirements that are applicable on the design. For example, the hot surfaces in a unit will not exceed the auto-ignition temperature of the refrigerant minus 100 K. In terms of temperatures, you can see here some examples. So for R290, for example, this means that hot surfaces cannot exceed 370 degrees. Also, the electrical components that could be a source of ignition should be handled. If they are indeed a source of ignition for that type of refrigerant, you have to apply EN 6079, which is there for explosive atmospheres. The piping installed for systems using inflammable refrigerants inside an occupant space shall be permanent except for connecting the indoor, and then also instructions and markings shall be provided. There are also requirements in part 3 on the installation site. You can see that part 3 is actually subdividing the several locations. We have requirements for open air, occupied spaces, unoccupied spaces not designed as a machinery room, ventilated enclosures, machinery room requirements, and piping in duct or shaft. I will not explain in detail because I have timing constraints, but I think it's worthwhile to look at it later on. And then in part 4, the requirements are in general set how to make operation instructions, how to make a logbook, what are maintenance and repair requirements for changing the refrigerant type and in service inspection, and also the requirements for recovery, reuse and disposal are explained, how to store refrigerant, and guidelines for repair of equipment using flammable refrigerant. So this concludes my speech explaining 5149. And I thank you for your attention.
Thank you, Els, for your presentation. Our next speaker is Dennis Dorman. Dennis is presently involved in consultancy with work with the Train Company. He's the chairman of ASHRAE Standard 15, and he's currently working on the Refrigerant Technical Option Committee assessment. He has over 38 years of working experience with Train. He has a broad product development experience in commercial products, special applications for nuclear power plant, plus extensive international experience. Dennis holds an MBA from the University of Wisconsin, La Crosse, and a Master in Mechanical Engineering from Georgia Institute of Technology. Dennis?
Thank you, Kareem. And I'd be remiss unless I said thank you to Eamon and the rest of the organizers of this conference. It's a pleasure to speak to you this afternoon. I hope I can add something, and in fact, you can absorb what I'm going to say. You know, if you're like me, you've been sitting there for, you know, the better part of 2 days and maybe can't quite absorb what you'd like to, but I hope you do. Before I go on, I need to say that just like some of the others, I have a disclaimer as well. I speak as an individual today. While I chair ASHRAE 15, and I certainly hope to guide and influence their work, ASHRAE is a body that creates standards through a consensus process, and so I can only represent what's going on in that consensus process. It is highly democratic, and you know, no single person can quite say where that consensus process might lead us. Els Bart showed you a version of this. I only want to add one thing. Throughout the last couple of days, we heard the A2L refrigerants being referred to as mildly flammable. Els got it right. Okay, it's lower flammability. Mildly flammable tends to distort the picture of A2L refrigerants, and I'll show you that in just a second. You know, as a matter of fact, it can be analogous to the difference between gasoline and lighter fluid, perhaps. The things that happen as these A2Ls ignite certainly can be different than higher flammability refrigerants, but they are flammable nonetheless. And the point is, really, we need to treat them with respect and understanding. And that's really the rest of my discussion. What are the underlying physics that govern how these refrigerants may be ignited, and what happens when they can get to the conditions that might be ignited? I think you saw several versions of this by at least the fellow from Honeywell. This is a chart of minimum ignition temperature versus burning velocity. It shows the 10 centimeter per second limit, and you can see that the A2Ls are in a class all by themselves, quite distinct from the A2 and the A3 refrigerants. And so this would lead us to believe that we ought to be able to create a line, and indeed ASHRAE 34 and ISO 817 created a line at a burning velocity of 10. However, notice that we're on a log scale here, and that ignition energy covers quite a range, and that gets back to my earlier remark. These refrigerants are flammable. They can be ignited. Without going into too much detail, there's quite a difference between the minimum ignition energy that can ignite this large class of refrigerants. There's not many in the class, but there's a huge difference in ignition temperature, in minimum ignition energy. And I think that was talked about by the gentleman from Honeywell. Some of them can be ignited by relatively common sources of ignition, and others are very difficult to ignite. But nonetheless, within the class, we have to treat all of them within that class, and therefore we must cater to the lowest ignition energy. Okay, so Els tried to explain what the end looks like in 5149. ASHRAE 34 gave us a definition. They created a class of A2Ls. Our job within ASHRAE 15 is to understand the underlying physics, much as the people that created 5149 did. You heard mention of Denis Cloic. I think Kotoka-san did some work. So, you know, there was some understanding and some research that went into building 5149. So too, we've tried to go back and revisit some of the underlying physics to understand how these refrigerants behave. Oops, I did something back. I need to go back. So two things help us understand what's going on here. Number one, we want to use dynamic modeling. We want to take a look at the underlying physics, and then we want to try and mitigate the consequences of a refrigerant release through ventilation. Ventilation is a very, very powerful thing, and I'll show you that. Last but not least, any discussion would be incomplete unless we talked about risk assessment. I'm only going to add just a couple of things about that at the very end. People have talked about risk assessments extensively. Inherent within ASHRAE 15 is an underlying philosophy, and that is we don't want to have a code that's very complex. It lives within a particular framework in North America where we expect a high degree of enforcement and, in fact, uniform enforcement. That's a little different than the collage of enforcement that may exist with 5149. So, again, ASHRAE 15 lives within a very particular framework in the United States. We want it to be clear and unambiguous. We want it to be simple, highly enforceable. So that leads to a concept that we want it to be safe by design, not by administrative rule, safe by design. We want it to be bulletproof, simple, enforceable. How do you accomplish that? Well, underlying ASHRAE 15 is a RCL calculation, and that is the recommended concentration or refrigerant concentration limit for the refrigerant. In the case of A2L refrigerants, it's set at 25% of the LFL. In other words, this entire room, if it was being fed by a system that had an A2L refrigerant in it, if that refrigerant was fully dispersed in this room, it could not possibly